Hi. Okay, very exciting. So the fifth chapter, the final chapter, and we're going to start in today. And always nice to feel like like you're moving forward. Okay, so the first material of this chapter is that we're going to do a review of big O notation. Now the emphasis here is on the word review. So we're talking about doing material that I expect that you've seen already. If you haven't seen it already, of course, you could look through the book and see if you can make more of what's in the book, or if not, you'll have to go through and look at whatever text you learned it from the first time. Okay, so ready for a couple of definitions here. Let's see. The the critical definition is the one that says that's here. The one that is, there we go, the one that is about big O. But in order to do this definition, I need the first definition. So the key point here is that it says a complexity function is one that inputs real number arguments and outputs real number arguments. So the inputs and outputs are real numbers, not what you might think, not natural numbers, but real numbers. Okay. The key idea here is that a function is a complexity function if it's eventually non-negative. So eventually non-negative means it may do some fooling around at 0 or at 1 or at 2. But by some point on, by some capital N on, by some point on, it's defined. So if you're looking at something like 1 over x minus 2, okay, so around 2, but at some point, from some point on, it's defined and you're good. And furthermore, from some point on, capital M, from some point on, it's positive. So we're not going to worry about writing absolute value bars. We're just going to assume that the function is positive. Okay, so then we're ready for the definition. The definition says that big O is a collection of complexity functions satisfying. Collection of complexity functions satisfying. So big O is actually a set, a collection of functions. Complexity function satisfying that there's constants capital N and capital C, so that if x is greater than capital N, greater than or equal to, then both g of x and f of x are defined so that we could compare them. If one is not defined, then we can't compare them. And furthermore, the comparison is that capital C times g is greater than or equal to capital F. So the idea with this is that if g is, say, 2x squared, and f is, say, 3x squared, that it's still the case that there's a constant, let's take capital C to be 2, that where you multiply 2 times 2x squared, and you're above 3x squared. Okay, so we say that f is an element of big O of g, or that f is big O of g, and that's the one that I personally use most often. Or that f is of order at most g, or another one, probably the one that's most commonly used in practice, is you say f equals big O of g. And the fact is that that's what you see in practice most often, but I like the other one. I like f is big O of g. And think of that as meaning that f's growth rate is less than or equal to g's growth rate. Okay, a couple of points about that. So the first is that Turing machines are discrete devices. So a person might sensibly say that we expect the functions to be natural number functions. Very, very, very sensible as a first try. But we find that, for example, being able to talk about the logarithm is convenient, and logarithm is most naturally a natural number function. Otherwise, you end up having to take the floor, the logarithm, this kind of stuff. But it's most natural to just say logarithm. So real number functions are convenient for that reason. Another reason that real number functions are convenient is because in just a minute we're going to apply L'Hopital's rule. L'Hopital's rule requires that you take the derivative, and taking the derivative requires that you have real numbers because you've got to take the limit as delta x goes to 0 kind of stuff. So it proves to be the case that on reflection, real number functions are more convenient than natural number functions. Second point, the term complexity function is not standard. I made it up, so don't expect to find it somewhere else. I think it enables me in the definition to get rid of all this stuff about eventually non-negative and move it to another place is basically all the reason it's there. And so in some statements further down, I can just say complexity function and I don't have to say eventually non-negative. The more substantive point is we use the letter O because this is about order of growth. And then finally, the hand-wringing part. F is big O of G notation. That's awkward, but perfectly standard. If somebody writes that, nobody's going to raise their hand and say, "What are you talking about?" It's perfectly standard. It's awkward for a number of reasons. Just as an example, you can write F equals big O of G, but you can't write big O of G equals F. It's a little weird. So sort of stuff. The F is big O of G, or F is an element of big O of G, is better. And not obscure. It's not like nobody will know what you're talking about, but it's not as common. The cold fact of it is, I have to confess that it's just not as common. Okay, anyway, enough hand-wringing over what you'll see when you go around on the internet looking at things. So the basic idea of big O, again, trying to get across in a review that what are the highlights, what are the big ideas. The basic idea of big O here is, I think, captured by these two pictures. Okay, so I'm thinking of big O of G as a set of functions whose growth rate is less than or equal to the growth rate of G. So the 2 points are, let's compare H to G here. So H is above G for a while, but eventually G gets to be above H and stays above H. So the first observation is that this initial nonsense doesn't matter. That's the capital N in the definition. This initial nonsense doesn't matter. We're worried about eventually stuff. Okay, so it has to do with what happens when you go to infinity. The second point about the definition is that here G is 3x squared, F is 4x squared, and a person might very sensibly and correctly observe that that F of x is always greater than G of x. That's true, but they have the same growth rate. They're both quadratic. They have the same growth rate. So the question says, is there a constant that would make G above F? Yes, the constant, for example, anything bigger than 4/3, how about 2, makes G above F. So if you can make G above F by multiplying by constant, I'm not talking about multiplying by X, I'm talking about multiplying by constant. If you can make G above F by multiplying by constant, then you say F is big O of G, or F is an element of big O of G, that kind of stuff. Okay, so that is to say these two really track together. These two do not. These two, or the two on the right, track together. Okay, so the two big ideas of the definition have to do with ignoring what happens initially and paying attention only to what happens eventually. And the second thing is about functions tracking together. Okay, so again, not doing examples of the definition because this is a review. So here are the algebraic properties that big O has. There's a list of what happens with respect to addition, what happens with respect to scalar multiplication, kind of stuff. If F is big O of G, then for any positive constant little a, the function little a times F is big O of G. So if F is big O of G, then 3 times F is big O of G. If F naught is big O of G naught and F1 is big O of G1, then the sum is big O of G, where G is the max of G sub 0, G sub 1. In particular, the important case, in particular, if F1 and F2 are both big O of G, then F naught plus F1 is big O of G. And then same thing for the product. If F naught is big O of G naught and F1 is big O of G1, then the product F naught times F1 is big O of G naught times G1. So it has all these nice algebraic properties, and if you take an x cubed and an x to the third, x cubed and an x to the fourth, then the result is going to be an x to the seventh type of property. Okay, so we say that two functions, these complexity functions, have equivalent growth rate, or the same order of growth. If oops, I put my pen down in the wrong place. If F is big O of G and also G is big O of F. So in that case, the picture that we had a couple slides ago, I won't annoy you by clicking back, but the picture that we had a couple slides ago of 4x squared and 3x squared applies, that the two track together. So they have equivalent growth rates of the same order of growth if F is big O of G and also G is big O of F. We say that F is big theta of G, or what's exactly the same thing, that G is big theta of F. The big O relation is reflexive, so F is big O of F. It's also transitive. If F is big O of G and G is big O of H, then F is big O of H. And then finally, having equivalent growth rates is an equivalence relation between functions. So if I say, for example, as I will, that 3x squared and 4x squared have equivalent growth rates, then you know that they sort of belong in a category of a bunch of other functions, all the x squared type functions, a bunch of other functions that all have the same growth rate. And here's the relevant picture down here. So we've got all of the complexity functions are inside this bean here. I picked a particular little g, some little g right there, some little g. And it's located somewhere in the bean. I happen to locate it there. I tried to draw here the collection, the set of functions that are all big O of g. So the collection is all the functions that are somehow less than or equal to growth rate compared to g. So if, for example, g is some kind of x to the fifth, well, then you'd see x to the fourth type functions and x to the third type functions and x to the one type functions and logarithm type functions, all the functions that have a growth rate somehow lower than g's growth rate. On the right there, I added a sketch for what does the cone below f look like if f is in g's cone, and it looks like it's subsumed. That's the transitivity. And then finally, all the way at the top here, I have this little area, and this is going to be the collection of functions that are not just in big O of g, but the collection of functions that are in fact big theta of g. So if you're in this little area up here all the way at the top, then you are big theta of g as well as big O of g. Okay, so we have sort of a hierarchy. Some things are above other things in some sensible way. And finally, the section here that is sort of the heart of what I want to review, excuse me. The heart of what I want to review is that how do you compute? If you give me two functions and say I want to compute whether one is big O of the other one, how do you do that? And the answer is, of course, the definition, of course, would apply, but the majority of the time we can apply the following theorem here. So you suppose that the limit of f over g exists. Suppose that the limit of f over g exists as x goes to infinity. That's the whole eventually story. F over g exists as x goes to infinity. And if that limit is 0, then g grows faster than f. If that limit is infinity, then f grows faster than g. And finally, if that limit is between 0 and infinity, then the two functions have equivalent growth rates. So there are three cases. The first case is that the limit of f over g goes to 0. So we have a fraction here. We have some kind of f over g. We have a fraction, and we're taking the limit as x goes to infinity. And we know what happens here with a fraction. So with a fraction, if the bottom is somehow stronger, then what's going to happen to the fraction as a whole? The bottom wins. Well, what happens when you have a large bottom and a small top? And the answer is you go to 0. Okay, so if g somehow wins, that means g is sort of somehow racing ahead of f. The g numbers are way bigger than the f numbers. Why then the denominator dominates. Try saying that 10 times fast. The denominator dominates, and so when the denominator dominates, you're looking at a limit of 0. If, on the other hand, the situation is reversed, if f is the stronger function, if the f values are way bigger than the g values, that is to say, f's order of growth is way larger than g's. If the f values are way bigger than the g values, why then the numerator dominates, and so you go to infinity. Okay, what about if they're tied? What if, like, the top is 2x squared and the bottom is 3x squared? If they're tied and you come out to 2 over 3, so neither the numerator nor the denominator dominates, why then what happens is the two functions are somehow the same-ish. They are big theta. Okay, so the theorem makes sense. That's the first point. And the second point is it enables you to do calculations because, who isn't good at taking limits as x goes to infinity? We can do all kinds of stuff with limits as x goes to infinity. The most important tool for taking the limit as x goes to infinity for our purpose is L'Hopital's rule. Most folks remember L'Hopital's rule from calculus, or a quick reminder will help you with it, is that what happens to the fraction of the functions is related by what happens to the fraction of the derivatives. So assume that f and g are complexity functions that both go to infinity as x goes to infinity, and such that both are differentiable for large enough inputs. So the usual stuff at the beginning. If f prime over g prime exists, then f over g exists and equals the same value. If f prime over g prime exists, in other words, when you compare the orders of growth, if when you compare the orders of growth you come up with a function, why then you can compare the functions themselves, or the fraction of the functions themselves. All right, and I'm not going to go through that because, of course, I have an example right here of applying it. But so basically here, f is going to be 3x squared minus 2x plus 4. G is going to be 1/2 x to the 5th minus 6th. If you try to apply the definition directly with capital N and capital C, you're in for some head scratching. But if you just do L'Hopital's rule, it's easy. Let's have a look here. So what's the limit of f over g? I'm trying to apply this theorem up here. What's the limit of f over g? Why, you can do that limit by observing that f over g is infinity over infinity. 3x squared minus 2x plus 4 goes to infinity as x goes to infinity. 1/2 x to the 5th minus 6 is infinity as x goes to infinity. Never mind the minus 6, never mind the minus 2, it doesn't matter. The whole thing goes to infinity. So this is an infinity over infinity limit. When you take the derivative, you get 6x minus 2, 5/2 x to the 4th, another infinity over infinity limit. But you've seen the trick now. What you do is you take the derivatives there. Derivative of 6x minus 2, derivative of 5/2 x to the 4th, and now this is no longer an infinity over infinity limit. It is now a 6 over infinity limit, and a 6 over infinity limit is very easy, 0. The overall conclusion here is that the denominator dominated. I like saying that. The denominator dominated. The denominator is somehow the stronger function, has the larger order of growth. So 1/2 x to the 5th minus 6 has a strictly larger order of growth than does 3x squared minus 2x plus 4. That is to say, f is big O of g, but it's not the case that g is big O of f. G is strictly stronger than f. F is below g, strictly below g. Okay, so L'Hopital's rule and this theorem makes it easy to do an awful lot of computations with the kinds of functions we find ourselves trying to compute. What you notice about that particular result on the prior slide, now I only did one example because this is a review, but if you do dozens of examples, you start saying to yourself, I always get an answer. I mean, one of them's above the other one. That's always the way it works. Isn't that odd? It is a little odd. That is to say, what we get then is a hierarchy, a strict hierarchy. It's not the case that A is below B and C is below B, but they're not comparable. That doesn't happen in these sort of ordinary kinds of functions we talk about. So that is sort of captured here by this result that logarithmic functions grow more slowly than polynomial functions, and polynomial functions grow more slowly than exponential functions. So there is a hierarchy of comparable, these functions are all comparable to each other, hierarchy of who grows slowly, who grows quickly. And just to take an example that compares things other than polynomials, I'll compare x squared and the log base 2 of x. And I'm going to do the L'Hopital's rule here. I won't walk through it so much. I've got an log base 2 of x on the top and an x squared on the bottom. That you have to look up the definition of log base 2 maybe in your calculus book, but there it is. There's the definition of x squared. And when all the smoke clears, I have only things in the denominator and a 1 is in the numerator until the limit as a whole is 0. That is to say, the denominator dominated. it is the case that x squared is it's the case that log x is big O of x squared, but not vice versa. Log x is big O of x squared, but not vice versa. Okay, so let's try the same deal with some exponential functions. So I have x squared and 2 to the x, and I happen to put x squared on the top and 2 to the x on the bottom. I'd come to a similar conclusion if I flipped them. It doesn't matter. So the derivative of x squared is 2x. The derivative of 2 to the x, again, maybe you have to look that up in your calculus book. The derivative of x squared is 2 to the x. The derivative of 2 to the x is 2 to the x times the natural log of 2. And, we take the derivative of the top and the derivative of the bottom again, and anyway, we get what we get here. I took the derivative of 2x and got 2, took the derivative of 2 to the x times ln of 2, and derivative of constant times 2 to the x, sort of stuff. So again, we find that the limit is 0. That is to say, the h function is the faster growing function. And when we look up here, the h function, which is missing a period at the end of the sentence, when we look up here, the h function is the exponential function. So we have a hierarchy. There are some functions that are above other functions, and we don't seem to find functions off to the side, or at least not obviously. That's what this slide tells us here. That tells us that we have a hierarchy of functions. Not a very good arrow. We have a hierarchy of functions where the faster growing functions are down in this table and the slower growing functions are higher in the table. If you have an algorithm that behaves this way, that's bad. If you have an algorithm that behaves this way, that's good. So log is a very good algorithm. Log is a good algorithm. Linear time is a good algorithm. Log linear is pretty good. N squared, okay. N cubed, okay. But now when you get up to exponential, 2 to the n or 3 to the n, no. Or n factorial or n to the n, no, those are bad algorithms. So we find ourselves able to linearly compare these functions. Okay, so we have a hierarchy, the Hardy hierarchy of functions. Okay, and the last slide here. I want to make a final point before we leave big O. And again, this is a review, but trying to hit sort of what are the big points. So the big point here is that we often split the hierarchy from the prior slide. We often split it between the polynomial functions and the exponential functions. So down here, I'm going to split this table. There we go. I'm going to split that table right there between the ones on the top and the ones on the bottom. And I got to explain why. Why am I making such a big distinction between the ones on the top and the ones on the bottom? Okay, so what is the table? So I listed some functions, the log, the linear, the log linear, the square, the cube type of functions, and looking at how quickly they grow. And I happen to be looking, I just picked a modern computer runs at about 10 gigahertz, which is 10,000 million ticks per second. And there's about 3 times 10 to the 7th seconds in a year. So the chart I took out, I used Sage, but anyway, I took out a way to compute for me, and I found out that, for example, if you use a log linear function, and you input data set of size 10, that your algorithm, your log linear algorithm, will finish in 1.05 times 10 to the minus 16 years. If, on the other hand, you have your data set is size 50, then your algorithm will finish in 8.94 times 10 to the minus 16 years. So the units for this table are years. Okay? All right, so again, I want to compare the ones on the top to the one on the bottom, and I'm going to draw a distinction. So I'm calling your attention to the final column. Okay, if you use an algorithm that runs in logarithmic time, and you have data set of size 100, then it takes 2.11 times 10 to the minus 17. And the next line takes, I know that it's a 3.17, but the important part is the times 10 to the minus 16. So it's about 10 times as long. Still pretty small though. This is about 10 times as long, again, still pretty small. This is about 10 times as long, still pretty small. This is, I know this is 100 times, but it's still, the overall 3.17 times 10 to the minus 12 years is awfully small. And then it says here on the bottom line, the exponential function, the function whose, the algorithm whose time is exponential will take 4.02 times 10 to the 12. That's not a typo. It went from 10 to the minus 12 years to 10 to the 12 years in one jump. In jumping from n cubed to 2 to the n, you went from 10 to the minus 12 years, which is, to 10 to the 12 years. Okay, well, how long is 10 to the 12 years? And the answer is that the universe is 14 billion years old, and a billion is 10 to the ninth years. So this exponential computation takes way more than the age of the universe. Way more than the age of the universe, even with a data set of size 100. So we draw a distinction between the ones below the line and the ones above the line, the exponential and the polynomial, because there is just a warp speed change in what happens when you go from polynomial to exponential. If you have an algorithm and you change it from, you have an algorithm and somebody comes and it's exponential and somebody comes along and says, wait, here's a polynomial solution to the same problem, that's just a massive difference. If you have an algorithm that is n cubed and somebody comes along and says, wait, here's an algorithm that's n squared, ooh, that's good, very good. But that's not the massive change that you see for the change between exponential and polynomial. Okay, so Cobham's thesis is that polynomial, that there's a distinction between polynomial and exponential, that polynomial functions are basically, okay, that if you have an algorithm that runs in polynomial time, okay, that's a first whack at a tractable problem. If a problem has an algorithm that runs in polynomial time, that's a first whack at the meaning of the word tractable. We can consider that problem, we consider to be, at least vaguely consider it to be doable. But if you have a problem whose best algorithm is exponential, then we can't consider that problem doable. Okay, so Cobham's thesis is that problems with polynomial time algorithms are tractable. So problems with polynomial time algorithms, problems with polytime algorithms, whoops, are tractable. Okay, are in some sense, at least you can vaguely consider them doable. But problems with exponential time algorithms just are not. Okay, very good. All right, so that's the review. Again, the book has more depth, and of course, the book is still also intended only as a review, but should give you, again, a better feel for what for the highlights of what Big O is about. Okay, great.